Okay, everyone's up bright and early this morning. Glad to see it. Okay, so we will today resume our sort of revised presentation of linear algebra that we started last time. So as I said last time, there's not much new that we're going to talk about here. A lot of it is notation with a few new ideas, or at least a more of a focus on things that you're already familiar with a specific point of view. Right, so remember the setup here. We have real vector spaces, finite dimensional. So things are very simple. And they have bases. So we have a basis for U, which we called F. Okay, and so then the idea was that if you have a vector V in V, then we write V as a linear combination, of course, of the basis vectors. Okay, and similarly, if U is in U, then you write U as a linear combination of the basis vectors. I'll use different kinds of letters for the indices for U and V, J, K, things like that for V, and A, B, and things like that for U. Okay, just because they're different dimensions. Okay, but in both cases, we're using the summation convention that we talked about last time. Okay. All right, and so remember last time that we defined the matrix of a linear mapping. So I have a linear mapping L from U to V, and I write the set of linear mappings by that symbol. Okay, so then we had the matrix, which I called capital L, and sometimes it's going to be, so if I call, let's say I abbreviate or use a symbol for this basis as F, okay, and a symbol for this basis as E, okay, then this matrix L, of course, depends on the bases that I choose, and let me just put the things in the right place in terms of whether they be up or down. And to denote that this matrix depends on E and F, and we're going to sort of do changes of bases today. And so it's going to be useful to use hang some notation off that matrix to denote its dependence on the bases. And this matrix is n rows, as we decided last time, and m columns, okay? All right, and remember the definition of this. The definition of this is that L of, and so let me just sort of reiterate again, that we write this matrix L like this. So it's L1, 1 up to L N1, and then L1M, and then LNM. Okay, so that's how we assemble the components, the n times n components of L into a matrix. And let me put these there. Okay. All right, and the definition of this matrix L is that if I take L and I apply it to a basis vector FA, that this is going to be L, A, J, EJ. Okay, so the idea was that FA is a vector in U, so L of FA is a vector in V, and so as a vector in V, it can be written as a linear combination of the basis vectors E, and the coefficients in the linear combination are exactly the entries in this matrix. Okay, so this is all stuff you saw in linear algebra, of course. Okay, and so notice. Okay, so let's say I take. I want to write down sort of in index form L of V. Okay, so V is any vector in, sorry, L of U. My map goes from U to V. Okay, so I take any vector U in U, and so I write this as L of U A F A, because every vector U can be expressed as a linear combination of the basis vectors. Now L is linear, okay, so I can, this is just scalar multiplication here by the, of the vector F by the scalar coefficient U. And so because L is linear, I can pull that outside. And so it's L of FA, okay? But that's just given by the matrix like so. And so this is L A J E J U A is how to write that. Okay, and so let me maybe write that, just change the order of things here. Let me write that instead as U A E J. Okay, so the point is that the components of the vector L of U, of course, are just the product of the matrix L with the components of U. Okay, and you can see here that why it is then that I need to put the components in the matrix exactly in the way I've done it, because when I do the matrix multiplication here, right, over the index A, that's going to mean multiplying by L11, L12, L13, and so on. So that's why I need to make the matrix look like this, so that it corresponds with our usual notion of matrix multiplication by a vector. Okay, all right, so as I said last time, we'll think about change of basis. And there's really, I'm doing this mainly to as an exercise in using the summation convention, okay, which is in full force here, okay? The summation convention is here being used twice, right, for summations over A and J, right? Okay, and so to be clear, this is an exercise in summation convention. And so you should view it that way. I'm not teaching you the change of basis formula because you already know that. I'm teaching you the summation convention. Okay. So now I have bases E equals E1 through En. And I also have a basis E tilde. It's not a very nice looking tilde. For E, and I have bases F and F tilde. Okay, so the bases E are for V and the bases F are for U. Okay, and so what do I know? Well, because these are both bases, what I know is that every vector in E tilde can be written as a linear combination of the vectors from E, and similarly F tilde and F. Okay, so I know that I can write E J tilde as a linear combination of the EJs. Okay, and the coefficients in that linear combination are going to be scalars, and sorry, I don't want to put a j there. Actually, I take it back. I do want to put a j there. Okay, actually, yeah, it would be clear as soon as I wrote it down. I don't want to put a j there because it's going to be a linear combination, so I'm going to be summing over that index, so it can't be j. And so I'm going to have some coefficient, a matrix out front here, and I'm going to call it p. Okay, and the indices on p are going to be like this. Okay, and these are chosen so that the free index of the one that's not being summed over agrees with the one on this side, and then I'm summing over k. All right, where p, okay, and I can, I assemble these in a matrix rather like I did up here. Okay, so it's going to be p1, 1 up to p1n. So p is square in this case. P n1 up to p n. Now, what do I know about this matrix P? So it's a square matrix. Do I know anything else about it? It's the change of basis matrix. What's true of change of basis matrices?
They're invertible.
That's right. So P is invertible. Okay. All right, and of course the same thing is true for F. Okay. I have F tilde A, and let me call the matrix for F. Let me call that Q, and that's going to be A B F B. Okay. All right, so this is also invertible. Okay. All right, so and so because these are invertible, what this means is I can, I can invert these relationships. Okay, that one and that one. Okay. And so when you invert these relationships, what you're going to get is you're going to express, here you're expressing the tilde basis as a linear combination of the untilted basis, and similarly here. You can just invert the relationship to express the untilted basis vectors as linear combinations of the tilde basis vectors. And the matrix that you're going to get out front is going to be the inverse of P. Okay, so you also are going to get that EJ is, and I'll write the inverse of the components of the inverse of P like this. Okay, and the F A is Q inverse A B F tilde B. Okay, so that's just change of basis, the change of basis formula going both ways. We're going to need both things. Okay, so now the question is, okay, so we have given L, a linear mapping from U to V, how are the two matrix representatives, okay, so L in F and E, and L in F tilde E tilde related. Okay, that's the change of basis formula. Okay, and you know what the change of basis formula is. It's depending on how you've defined your Q's and P's, the tilted one here is going to be some product of this, and you're going to pre-multiply it by, I have to think for a second to see whether it's Q or P, but it'll come out by, either P or P inverse, and then you pulse multiply it by Q or Q inverse. Okay, so we'll see how that all comes out. All right. Okay, so let's just use the definitions here and exactly see how the change of basis formula comes out. Okay, so let's write down. So what we know is we know that L F tilde E tilde is defined by it's defined by L of F tilde A is equal to L tilde A J E tilde J, right? Okay. So what we're going to do now is we're simply going to substitute in these relationships for the tilde basis vectors here, okay, and then fiddle around, okay. All right, so this means that L, all right, so I'm going to stick in F tilde. So F tilde is related to the F's by Q. So it's going to be Q, B, A, F, B, okay. That's just F tilde A is equal to, and I'm using summation convention all the way through here, right? So normally there would be summation signs on here, but again, this is supposed to be an illustration of exactly the summation convention. So, okay, and then E tilde is related to E's by P, okay? So E tilde J is going to be P, J, K, E, K. All right, and so you'll notice here in terms of using the summation convention, all right, so here I've used it, and what you notice is that I have to leave the free index on each side to be the same. A is free here, in other words, not summed over, so it has to be also free here. J is being summed over here, okay? Now, again, still, it's just a case that A on each side of this equation is free, okay, and on this side I'm summing over B, and so you need to, so sometimes when you do this the first time you get yourself confused, and you maybe don't introduce a new variable to sum over here, okay, but you have to introduce a new variable to sum over. It can't be A, so let's make it B. Okay, and then similarly on this side of the equation, so I have EJ, and this whole thing is just EJ. Okay, and so the J is being summed over. Okay, just I'm inheriting that from here, and then I need to also introduce a new summation index, which can't be J, so I'll make it K. Right, so it can't be that I'm summing over J here, because I'm already summing over J here, and to do that more than twice violates the summation convention. Okay, so the summation convention guides you on how to do these calculations. If you just apply the rules, and introduce new variables when you have to, make sure that summation only happens over pairs, and that the free indices on each side have to match up. Okay, all right, so anyway, let's continue on with this. Okay, so L is linear, and so I can pull the Q outside. So this is Q, B, A, L of F, B, okay, is equal to L tilde J, A, P, J, K, E, K. All right, now what I want to do is I want to bring, I want to cancel the Q on this side, right? Because I know that I have a formula for, sorry, where is it? Yes, I have a formula for L of FB, which is the definition of the matrix representation of L in the untilted basis, right? So I want to get rid of that. So what I'm going to do is I'm going to multiply this equation by Q inverse, okay? So when I multiply it by Q inverse, okay, and I'm going to leave the sort of indices off here and put them on afterwards, after I kind of write everything else down. Sorry, Q. All right, so again, I'm going to put the indices on that in a second. So this is L tilde J A P K J E K. All right. Okay, so now I want to put indices on Q inverse. And how am I going to do that? Well, what am I going to, remember, I'm multiplying Q inverse by Q, okay? So the B on Q is already being summed over, so the free index here is A. So what that means is I need to put an A up here, okay, because to give me matrix multiplication. Okay, and then I'm going to get a new index down here, which I'll call C. Okay, so you know that's how you do these calculations. All right. Okay, now what's this? Well, these are the components of the matrix Q inverse Q. Okay, what are the components of the matrix Q inverse Q?
Identity.
Yeah, so Q inverse Q is the identity matrix. So the components of Q inverse Q are the components of the identity matrix, and those have a special name. So notation. The symbol is what's called the Kronecker delta. It's nothing elementary. Again, the best way to think about it is that it is the component representation of the identity matrix. So this is called the Kronecker delta. Okay, and it's delta JK. Okay, and so you can use any up here. I'm actually going to apply that not with JK but with A and B, but it doesn't matter. Okay, and so this is 1 if J is equal to K and 0 otherwise. Okay, so this is the This is the index representation of the identity matrix. Okay, right. So this means that there's ones on the diagonal, right, where the two indices agree, and zeros everywhere else. Okay, so that's the identity matrix. So the point is now, when I do this multiplication here, I'm going to actually get this. This whole thing is simply going to be, remember, A here is being summed over, so this is going to be delta BC. Okay, so I get delta BC L of FB is equal to, okay, so nothing over here changes. So it's Q inverse AC L tilde J A P K J E K. Okay, good. All right, so now we can simplify this still further. What's this? This is actually something very simple. So remember here, I'm summing over B. And this summation, the definition of delta is that this summation, although it's a sum from 1 to M, actually only has one non-zero term in it, right? And that's when B is equal to C, just by the definition of the Kronecker delta. Right. So the point is that this sum just gives you L of FC. Does that make sense? So this is L of FC, and nothing over here changes. Okay. All right, so the rule that you use here, and it's not really a rule, it's just kind of just follows immediately from the definition of the Kronecker delta. But anytime you sum over an index of the Kronecker delta, as I'm doing here with B, essentially the upshot of that is that you just swap the index here with the index here. Okay, that's sort of what happens. And again, it's not really a rule. It's just the definition of the Kronecker delta. Okay, now I'm almost done, right? Because I know what L of FC is. L of FC is LC, okay? And so I'm just going to use the definition of the matrix representative in the basis, the untilted basis. And so I get this. Okay, and over here, actually, let me make I made the right choice here, but there's no reason I should do that necessarily. Let me make a wrong choice, and it's fine. I can do that. Let me use J here, and you'll see how to fix that wrong choice up, and in a way that just totally doesn't matter. But sometimes it's helpful to think about it beforehand. Okay, so everything I've written here is correct. Okay, none of the rules of the summation convention are violated, right? So in each of the terms here, all of the rules of the summation convention hold. I'm summing over repeated indices. One's a superscript, one's a subscript. Similarly over here, over here, the expression is a little bit more complicated, but I'm summing over A, and I'm summing over J, and I'm summing over K. Right now, so as I said, this actually wasn't the, I chose J here. It doesn't really matter what you choose, okay? As long as it doesn't appear anywhere else in this expression, right? Because then you'll violate one of the rules of the summation convention, okay? But what would I like to do? What I want to do is I kind of want to balance or look at this equation, and I want to read off what's this expressed as a function of this. Because remember, that's what I'm trying to do. I'm trying to relate the tilde matrix with the untilted matrix. Well, actually the other way around. I'm trying to relate, it turns out, the untilted matrix with the tilde matrix, okay? And the way I'm going to do that is I'm going to use linear independence of the basis here. Okay, and if you have an expression which is equal to 0, and the expression is a linear combination of linearly independent vectors, then the coefficients in the linear combination must be 0. So I kind of want to do that, right? But the problem here is that it's an EK here and an EJ here, but this is just a summation. J is just a summation index, and I can call it whatever I want. And my point is that I may as well call it EK, because then I have EK on both sides. All right, so sometimes you'll write these things down, and then you'll realize that you made an unwise choice of a summation variable, and you get to change that. Okay, it's just, if you were to write this, it's the same thing as saying, oh, sorry, J and K, right? Those are obviously the same thing. And, it's like an integration variable, right? We'd call your integration variable whatever you want. It's the same idea, okay? But if you make the smart choice here, then you can combine the two equations, and then what you get by linear independence of the e's is you get that L, K, C is equal to Q inverse A, C, L tilde, J, A, P, K, J at the end of the day, right? So that's the formula that we wanted, because it relates the untilted basis to the tilted basis, okay? And then you see that the change of basis matrices show up here. So maybe let's try to write this in a way that's more familiar to you, because this is just written in component notation using the summation convention. And you normally, I'm sure in 212, when you did this, you didn't write it like this. You wrote it as actual matrices that you were multiplying together. So let's try and do that, okay? So this says that the matrix on this side is, of course, the matrix representation in the untilted basis, which is this. Okay, so what we need to do here is we need to sort out what's the matrix multiplication that's going on here. Okay, am I pre-multiplying by Q inverse, or am I post-multiplying by Q inverse? Well, the way to sort that out is to remember, so I'm going to scroll back up here, is to remember in this formula here, okay? when I'm doing multiplication of a matrix by a vector, and it's going to be the same thing when you're doing multiplication of a matrix by another matrix, this summation over the subscript means that this thing is on the left and this thing is on the right, okay? Because this is really the matrix LU, okay? Well, actually, let me be a little bit more careful about that. Oops. This is really the matrix L times the matrix U. Okay, where the matrix U simply means the components of the vector U. Okay, and so the point is that this tells us the order in which the matrix multiplication happens. The lower index goes on the left. Okay, so we're going to apply that down here. Okay, all right, so let's look at this expression. So I'm actually working this out myself, so because I can never tell when I look at these things. And the fact is, it kind of doesn't matter, but just to connect this to what you already know. So I look at the summation over J here. Well, according to the rule that I just wrote down, this should mean that P goes on the left of L, okay? So this should be P, the matrix P times the matrix L in the tilde basis. Okay, and then the other thing being summed over here is A. And so again, the lower index kind of means it goes on the left, and then the upper index means it goes on the right, so that works out. So this is Q inverse. Okay, so that's probably the form that you derived in 212 for the change of basis formula, right? So you had a pre-multiplication by something and then a post-multiplication by the inverse of something else. Okay, but again, this was mainly just an exercise in summation convention. Okay. Because we're going to be doing all kinds of summation convention calculations. So it's good to do one that's connected to something you already know about. Okay, and so like I said, I had to think a little bit about going from here to here in terms of the order of the matrix multiplication here. But the fact is, it kind of doesn't matter. This formula is just fine, and you know the semantics of which matrix goes on the left and which one goes on the right kind of doesn't matter. This expression has meaning independent of representing it like that. Although, like I said, to represent it like this, at least that makes it look more familiar to you. Okay. But we're going to be writing things like this, and we're just going to leave them like that. We're not going to try to understand them in terms of matrix multiplication. Okay. All right, so one of the things that we're going to talk about are dual spaces. So dual spaces are very simple on the one hand, but on the other hand, they're so simple they're confusing. So it's one of those kinds of things. And it's actually difficult to explain it in a way where you get that it's not as simple as you think it is, okay? So I will try to do that. Okay, so the idea of a dual space is very simple. So if V is and let's see again, just stick to the finite dimensional case for simplicity. And the dual I denote by V star. And it's simply the set of linear maps from V into R. Okay, so it's a simple enough thing. Okay, so for those of you who happen to maybe know a little bit or more math than you need to do this course. Duals play an important role in a functional analysis, and then when you do that, you're going to be thinking about not just finite dimensional vector spaces, but infinite dimensional vector spaces, which may have, for example, norms. And then what you want to talk about here is the set of continuous linear maps from V into R. Excuse me, and in that case, the actual dual here depends on how you put a norm on V. But in finite dimensions, everything's simple, and the dual is absolutely unambiguous. Okay. All right. So now what we want to do is we want to represent elements in the dual space in the right way. Okay, and what do I mean by represent? Well, I mean choose bases for everything in sight. Okay, and so when we talk about manifolds, that's going to be equivalent to choosing coordinates. Okay, and we want to see when we choose bases, what do things in V star look like? Okay, so we know what linear maps look like. Linear maps look like this, or in component form like this. Okay, what about dual vectors? Okay, so the first thing is we're going to define a basis for V star. So let's maybe think for a minute about what is the dimension of V star? What is the dimension of V star, do you think? Well, if you have linear maps from an m-dimensional vector space, let's say, to an n-dimensional vector space, so we know that the set of linear maps is a vector space. Okay, so it has a natural vector space structure, and you would have studied that in 212. So this is a specific instance of that. Okay, what's the dimension of a vector space between the vector space of linear maps between an m-dimensional vector space and an n-dimensional vector space? Well, remember how you represent a linear map. You represent a linear map with a matrix, and it's a matrix which, as we've seen already, is n by m. So really what I'm asking you is how many components are there in an n by m matrix? Having made the question that easy, I absolutely expect an answer.
M times n.
Thank you. Okay, so in this case, V is n-dimensional and R is one-dimensional, and so it's n-dimensional. Okay, so V star has the same dimension as V, and so it's going to have the same number of basis vectors in any basis as are in V, namely n. Okay, so now, given a basis E1 through En for V, define Ej. Okay, so now you either love this or, well, you either like it or hate it. So what I'm going to do is I'm going to write things which look exactly like E's, except they're going to be the location of the script will be different. For the basis vectors, I use a subscript, and for these guys, I'm going to use a superscript. Okay, but the same letter is there to indicate that these two things are closely connected. Okay, so I'm going to define EJ. This is going to be an element of the dual space. Okay. And I give you a formula for it. Okay, so EJ of a vector V, okay, so remember that an element of the dual space, by definition, is a linear map from V into R, okay, and so therefore EJ is going to take as an argument a vector V, and that vector V I'm going to write, of course, as a linear combination of the basis vectors for V, so V, K, E, K, okay? And this is equal to, my definition of EJ is that this is going to be VJ. Okay, that defines EJ. So what this really means, if you want to sort of give some kind of geometric meaning for what EJ is, so EJ is the jth component function. Okay, and what I mean by that is it's just exactly what this formula says. You give it a vector V, and it returns the jth component of V in the basis E. Okay, right. So it depends on the basis that you choose, of course. Okay, so I can do this for every J. And I get this collection of vectors, then a collection of vectors in the dual space, E1, E super 1 up to E super n, and I claim that that's a basis. Okay, so let's prove that. So what do I need to do to show that it's a basis? I need to show that it's linearly independent, and I need to show that it spans V star. So in fact, I don't actually need to do both of those things, right? And the reason I don't need, it suffices to do one of them. And the reason it suffices to do one of them is I know that the number of vectors here is the right number of vectors. So it's, I know that V star has n dimensions, and there's n vectors here. So if I can show either that they're linearly independent or that they span, then one of those things will imply the other, just because the counting works out. All right. However, I'm going to do both things because, again, it's a nice exercise in using the summation convention, and it also gives you a little bit more intuition about how these dual elements of the dual space work. All right. Okay. So first, we're going to prove linear independence. How do you prove that something is linear, or a collection of vectors is linearly independent? Well, you write down a linear combination of them, and then you show that the coefficients in the linear, if the linear combination is equal to 0, then the coefficients in the linear combination must be equal to 0. So I'm going to write down a linear combination of the E super J's. And set it equal to 0, right? So that's what a linear combination looks like using the summation convention. Okay. So I want to show that as an element of V star, that sum being 0 implies that each of the coefficients is equal to 0. And how I'm going to do that is I'm going to just evaluate this element of V star. Okay, so this thing is an element of V star. And what that means by definition is that it takes a vector in V and gives you a number. And so what I'm going to do is I'm going to feed this thing a specific vector in V. And it's obvious what that specific vector should be because there's only one collection of specific vectors we have lying around, and those are the basis vectors. Okay, and so this implies that Cj, Ej. Okay, now I need to put an argument in here, and the argument I'm going to put in is one of the basis vectors, and it can be any one except Ej, because if I put it in Ej, then I violate the summation convention. So it's going to be Ek. All right. So what is Ej of Ek? Well, by definition of Ej, Ej is the jth component of the basis vector Ek. What's the jth component of the kth basis vector?
0.
Unless? Is it always equal to 0? Remember that there's a summation happening here over j, right? Okay, so j runs from 1 to n. Okay, and so in particular, included in this summation is going to be k, right? So there will be in this sum a term which is ck ek of ek. What will that one be?
1.
Yeah, exactly. Well, ck, but yes, exactly. And so this is going to be. So the point is that this thing is 0 unless j is equal to k. But that sounds awfully familiar. Okay. So this is cj delta jk. Right, and so now I apply my rules about summing over Kronecker deltas, right? And this just is ck. Right, so that shows that each of the coefficients in the linear combination must equal 0. Okay, so again, that actually does it. I would be finished right now, but I'm going to just show the spanning property because I think it's illustrative to do that. Okay, so what I need to do is I'm going to take an alpha in V star. Okay, and what I need to do is I need to show that alpha is a linear combination of these guys, which I'm trying to show are a basis. Okay, so I'm going to write alpha equals. Okay, so alpha is going to be some linear combination of the E super J's. And let me write out this linear combination, not using the summation convention for a second, just because it's easier to understand when you are just initially seeing this. Okay. Okay, so there's going to be some coefficients here, and I need to figure out what these coefficients should be, because that's what it means to show that something spans, is you have to show that coefficients exist here. Okay, and so there's a rule of mathematics which very often applies, and that is that you collect all the data that you have in front of you, and then you do the only thing possible. So what do I need to do here? What I need to do here is I need to come up with n numbers, okay, from the data that I'm given. Okay, and I claim there's only one way to do that. Okay, because what's the data that I'm given? The data that I'm given is, well, alpha, okay, and a basis. That's the only data I have. Okay, so given that data, there's really only one way to build n real numbers, right? And what is that one way? Well, it's alpha of E1, alpha of En, like that. Yeah, it's the only way you're going to construct n numbers. And so, that's your first guess, right? So you have to prove that that's correct. But nevertheless, that's sort of, often doing this will give you the right answer. Okay. But it doesn't constitute a proof, of course. All right, so what I'm going to do is I'm going to claim that this is true. Okay. So this is my guess, and now I'm going to prove that my guess is correct. So what do you need to do to show that it's true? What you need to do to show that this is true is you need to show that if I evaluate the left-hand side and the right-hand side on any vector in V, I get the same thing back, right? Because then they will be equal as elements of the dual space, because the dual space takes vectors in V and gives me numbers. So if I take an arbitrary vector V and feed it into here, and an arbitrary vector V and feed it into here, and I get the same thing, that shows that they're equal. Okay, so let V be in V. So I'm only it's 9:20. I'm going to be 1 or 2 more minutes. And of course, I'm going to write V as a linear combination of the basis vectors. I'm going to use K here because I'm using J in the expression above. Okay, so then alpha of V is alpha of VK EK, which is because alpha is linear, I can pull the this is just a summation of a scalar with a vector, so I can pull the scalar out front. So this is VK alpha of EK. All right. So that's one. That's what I get when I apply the the left-hand side to V. What about the right-hand side? Okay, alpha of EJ. EJ. Okay, so this is an element of V star. The whole big thing is an element of V star, and the element of and I'm going to act on the element of V, which is V. And so I'll write it as that's what it is, like so. Okay. All right. So again, this is an element of V star. This is scalar multiplication. Elements of V star are linear, so I can pull the VK out front. Okay. And then I'm going to get alpha of EJ. Okay. And then it's going to be EJ. Well, and maybe let me leave the, sorry. Leave the parentheses there. So it's alpha of EK, right? Well, the parentheses will go away in a second. Okay. Now, again, I just have scalar multiplication here of this by this, and so I can take this parentheses here, and I can really just move it to there. Okay, so I get VK alpha of EJ, then it's EJ of EK, and I've already shown that this is just delta JK. And using the rules about swapping sums of delta of indices on deltas. So both of the indices on delta are being summed over here, both J and K, and I can choose whichever one I want to substitute out. It makes no difference. I'm going to use K because I have K up here already. Okay, and so what I've shown then is that alpha of V is equal to alpha of EJ of V for every V in V, which shows indeed that alpha must be equal to alpha of EJ. Okay, and so in other words, it shows that it shows that the EJs span because I've taken any alpha and I've written it as a linear combination of the EJs. So I'm done. Okay. All right. So sorry, I ran a few minutes over. We'll continue on with this next time. I will stop the recording.